Okay, so I'm going to try to do an entire video that explains how to do thrust vector control or adaptively steering a rocket. So it basically comes down to, I would say, three things. The first is you need a dual axis gimbal. That's basically a way of moving the motor in different directions so that you can compensate as it as the rocket moves around. Then we need to do rocket design, which is actually pretty simple and you don't have any fins. This is a rocket. And finally, you have to make a control algorithm. So how do you figure out how to steer? So those three things. See if I can do it in this one video. Okay, so this is a dual axis gimbal. So that means I can rotate it in two different directions. So like this is X. This one over here will move it in Y. So it's actually pretty simple. There's just two cheap random servos. They'll do the job. And it's a lot of iteration. So like I'll start figuring out how to build a centerpiece and then 3D print it. Then it doesn't quite fit, so I print another one. And then there's another piece that will go around it and you just iterate. So I'll take you through the CAD. Okay, so we're using Freecad, which is my favorite tool for CAD. It's not great, but it is free. And I got this thing modeled up, so I'll share how this kind of works. So first, the first thing is just the rocket holder. So you just figure out what engine you're using. I'm using SD's E9, 24 millimeter, I think. So, you know, it's pretty simple. You make a cylinder, subtract out the center, and then print it. You have to iterate a couple times because you know there's a tolerance and you want to get it to fit. But this part's pretty simple. And then here is just start adding screw bosses. So again, when I'm doing this, I don't really know if it's going to work, but I know if I'll find what doesn't work right away, and then I can iterate on it. So this is the first piece. Then here's a little push point for a linkage stopper. You can Google that, but enables us to kind of use the servo to push it. So once this looks about right, then yeah, so this is the first piece I would model. So I just put screws in here. That's going to allow it to rotate in this direction when the servo pushes it. So I need a piece that's going to hold the servo. So I'll just model this guy up in there. Again, I pretty much model everything with just cylinders or blocks, so nothing too important here. And then this part, then the next servo is going to have to kind of push into something else. So we'll have another linkage stopper up here. But anyway, so these last pieces, that's going to be part B. So this enables rotation in this direction. Then we're going to have to put another piece around it that enables rotation, you know, 90 degrees away from that. So if this rotates in X, the next piece will add in Y. And again, I don't get this right on the first time. I screw it up, reprint it, then I'm done. Okay, so then this piece will go around here. So again, this is previous one rotated here. I'll screw this one in like this. And we need to hold the servo. And then I add this just so I can install it in the rocket. So I'll put this here. This is actually something I'm going to glue straight into the rocket, which is a 4-inch tube. And then I can just kind of screw this guy all in there. But anyway, so I'll put all the Freecad and the STL files. I'll go ahead and put those on the GitHub. Okay, moving on to the next part, we have to design the rocket. So I like simple. So I have a tube and a nose cone. I didn't put any effort in the nose cone, I just made it a triangle. I don't care, I almost thought about not even doing that. But I like no fins. Fins are complicated. It's supposed to have adaptive control, so what do I need fins for? So the only thing we need to care about is the CG, center of gravity, versus CP relationship. The center of phase should be farther down on the rocket than the center of gravity. So easy enough to find the center of gravity. You just see where it balances. Center of phase, we can use OpenRocket. OpenRocket here, so make a nose cone, conical. It's 5 inches long, 4-inch diameter. Pretty cool. Add a body tube, 18 inches long. Boom, and our rocket is modeled. So we see here, it says the center of gravity is there, it's okay. Center of phase, it says is up here. So obviously, this is nonsense. It doesn't know how to calculate it. You know, it's a good rule. Simulation tools are only as valuable as, you know, if you know how to use them. So in this case, it doesn't know what it's doing, and we have to kind of do it by hand, but it's actually pretty simple. Okay, so if you want to know how to calculate center of phase, so it's true for any rocket, the area of the rocket times the center of phase is basically equal to the sum of the area times the center of phase of each individual component. So I only have two. I have the body tube and the nose cone. So area of the tube times the center of phase of the tube plus area of the nose cone times the center of phase of the nose cone. So we can calculate this pretty easily. So the total area of the rocket is, area of this, 18 times 4, plus the area of the triangle. You can figure that out real quick, 5 times, now you can figure it out. And we don't know the center of phase as we're solving for, equals the area of the tube times where the center of phase of the tube is. We know that it's right in the center, because it's a tube. Area of the nose cone times the center of phase of this. Now it starts at 18 inches plus 5/3. So the center of phase of a triangle, by the way, is just 1/3 of the distance. So that's where this comes from. So you solve for this and you get center of phase is 10.3 inches, or basically just north of the center line. So now we know that, so wherever we put our center of gravity, it just needs to be a little bit north of here. So I just add a little bit of weight to the nose cone and we're fine. We don't need fins. I don't want a lot of stability because again, I'm not relying on wind or air pressure for aerodynamic stability. Okay, so how do we design the control system? So let's real quick talk about what's going on. So if you know, torque is inertia times alpha. That's kind of like F equals ma, but for rotation. Inertia, go look it up. And then I write alpha as the angular acceleration, or the rate at which the speed is changing, or the second derivative of theta. So I model the rocket, say it's going up this way, we want it to go straight up. It's at a theta angle away, which we don't like. So we have torque, which is basically perpendicular force times the distance from the center of gravity. So that's a function of how much power is perpendicular, the force is perpendicular. It's basically the motor thrust times sine of phi, which is how far you're displacing this. So in this case, you would push the motor up, it would spew out, that's pushing this direction, it would right the rocket a little bit. It would move the rocket to want to spin that way. D, you can just measure by where your motor spins versus the center of gravity. So this is the equation of motion. So how are we going to do the control algorithm? We're going to use PID controller, really just a PD controller though. So proportional means like the farther the rocket, if this is the rocket, you want to go up. If it's at an angle like this, you would apply more torque to try to get it to go this way. And that's fine, but once you start it turning this way, nothing stops it. So you need to actually break it or stop it. That's why you have derivative or angular speed. And so basically as this thing starts going this way, you're going to compensate by trying to, oppose that torque so it'll actually stop. And then integral, that kind of, if you have a long burn motor, it would help like if there's any systematic offsets in your design, that would kind of help out. But I don't really use that one. So we're trying to right the rocket by iteratively tweaking it back to the center, but also knowing that nothing's going to stop it if we start swinging it this way. We need to make sure we're ready to break it, and that's why the derivative or angular speed is there. So I don't have Simulink or any tools, so just make our own differential equation solver. It's actually pretty simple. So let's say, theta is the angle of our rocket. It'll be at time 0, time 1, blah, 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 blah. We just need to figure out where it's going to be. So we have the equations of motion from the top. Remember, torque is I times the rate of change of the angle, the acceleration of the angle. So the rate of change of theta with respect to time, that's just, we can approximate that with a simple derivative, time n minus 1 over delta t. Same thing then for the second derivative, we can just basically get a simple equation for what theta is in terms of the previous states. So we go through, we solve all this, and our equation of motion is torque equals I times theta dot dot, forgot an I here, your inertia. So this is what torque we're applying. So we own this part. We get to decide what goes in here. And the way the system responds is over here. So basically we're just gonna make some code that goes through in steps and will update the position of the rocket, the angle, as a function of what torque we're applying to it. I call it PID.pi, so I just define a bunch of constants. So the inertia of my rocket is this. I'm going to step as small as 20 milliseconds. The force, here I actually pull the force on the rocket, so whatever your force in newtons is a function of time. But essentially all I'm doing here is, the torque is what angle we set it at. Theta gets updated per the equation we just derived, and then I calculate it, and it just repeats over and over and over. So I can run this test, and I give it an initial start angle. The black line is theta, so I can see how it responds. The blue is actually what angle the motor thruster should be set at, so it's kind of compensating. And by varying the control parameters, Kp, proportional, derivative, and integral, I can kind of figure out what the right values are, and that's how I figure out what PID constants to use that'll actually write the rocket. There's not a whole lot else to do for a launch stand. I had this chemistry stand in my garage, and I'll use that. So I printed some little holders here to put it on here, so I have something to launch off of. In the top, there's just I have a battery and the charge for the black powder. The cone, a little bit of weight in there again to move the CG up. Parachute. So in here is Raspberry Pi, a lithium-ion battery, an IMU, which is BNO055, and then just a power adapter that converts the 4 volts on the lithium battery to the 5 volts the Raspberry Pi uses that basically controls everything. So with that, that's about it. I cut some holes in here so I can screw some stuff in or charge the battery, but that's it. So yeah, that was pretty good. A lot went wrong there. First thing, so the SD card on Raspberry Pi cannot handle vibration or shock. So what happened is, first of all, as soon as I launched, Raspberry Pi stopped logging. So the SD card wasn't working anymore. It was still able to control for a little bit. I'm not sure. The other thing is, I had in the script that it should select the desired angle based on where it is before launch, but I was actually holding it at an angle, so it set the target angle for like this. And I didn't realize that till later. So it actually went up, immediately tried to go to this angle, which was really cool. So, if you haven't taken a rocket to the phase, you haven't lived, so live and learn. But anyway, so corrected those things, and then soldered the Raspberry Pi's SD card down, add a little control loop where I can verify exactly what I'm doing before I launch, and then we go to launch the second one. Data. So we have pitch angle, which let's call it the angle about the x-axis. So blue is actually what occurred in the flight. So you see it starts to deviate down. We're trying to get it right about 0. It starts to oscillate. But you can see black is what the angle I'm using to try to compensate for that. So you can see it's compensating for the angle properly. So the algo is doing well. What's unfortunate is the error really starts to grow sinusoidally. Let's go on. So let's look at, that's pitch. Roll is the angle about the y-axis. We get the same kind of effect. So here I'm trying to get it, I have a bias where I'm trying to get it at minus 3.75, but same thing, it's compensating properly, but the angle error grows. It looks like what happened, here's a measure of the spin, or spin about the z-axis. It's actually rolling at about 200 degrees a second, which isn't too fast, like with 40 RPM or whatever. But pretty sure that's what's I gotta compensate for, because then the angle that we're trying to grab is continuously moving. Anyway, there it is. Thrust vector control. Next step would be add some sort of spin stabilization. But that's it.